Hello. First, I want to welcome all of you for joining our virtual presentation. This is kind of new for us. Um, my name is Andrew Ferlitsch. I'm part of Google Cloud AI. I belong to developer relations. As developer relations, we are external facing. You'll see me in a lot of places. I'm typically at conferences doing presentations. I might be out in the software at times in the software communities doing training. At times I'm being loaned to universities to be a guest lecturer. I also work with Google Cloud's really big enterprise customers. I help their engineering and data science teams get over barriers of taking machine learning into production. Beyond that, I do lots of other activities that are typical of developer relations. Um, had the opportunity in December to run a study on facial recognition cloaking. That is a black box adversarial attacks on facial recognition. I have opportunities to have early reads of papers from some of our Google AI researchers or just before peer review. I get opportunities to dog food some of our advanced data science tools before they're released. I work on developing new design patterns for deep learning models. And finally, I'm writing a book on deep learning through Manning. Okay, well, in this talk, I'm going to just give you an overview of what machine learning is like in production. And if you were in a large enterprise company, what would be expected of you? So we'll start with how it evolved. So 2017 is really when AI and ML was on everybody's radar. And at that time, worldwide, we had about 10,000 data scientists. And so the big companies were what we call in the planning and discovery phase. So planning was like, how do I make AI work in my product? Where are my products can I use them? What kind of data do I need? Discovery is like learning what kind of people do I need? What kind of methodologies? What kind of technologies and all that. And at the time, the principal roles involved were decision makers, engineering staff, and outside ML consultants who had existing expertise. We saw in 2018 in those companies, they had moved into exploration and prototyping. They were building models, trying them out, seeing what they do, making modifications, experimenting, and so forth. And the type of people involved now were expanded. You started to see senior engineering management. Typically, a senior data scientist has been hired as the lead. Data engineers are being brought in. They're connecting with the database team and a continued use of ML consultants with their expertise. 2019 was really an interesting year for the enterprise size companies. They're in full development and they're transitioning into production, and some of them actually went into full production. And again, you see an expanding set of roles. The chief technical officer, by now you're expanding the data scientist team with junior data scientists, bringing in more data engineers, bringing in ML operations, which is sort of the equivalent of DevOps, but for machine learning, and starting to use these third-party ML API services and working with integrated system vendors. 2020, everybody, all these enterprise companies are in or moving into full production. And now you have about 250,000 data scientists in the world and 2 million ML practitioners. The entire chief executive line is involved. It continue to grow other areas. Now they're using ML AI managed services and ML AI turnkey solutions from third parties. So let's kind of look at what's happened with the technology over that time. So in 2017, we were still mostly using what would be called traditional machine learning. And that would be like the cart analysis and the business intelligence, BI. And typical tools that people were using or frameworks were like scikit-learn and NLTK for natural language understanding. And the vast majority of the people involved had a statistics background. In 2018, you started to see deep learning coming in. And with that, the frameworks TensorFlow and PyTorch started using techniques as transfer learning, utilizing third-party ML APIs and managed ML managed training services. And you see an expansion of backgrounds to include now computer science people and people with data backgrounds. In 2019, that continued to expand. You start seeing more reinforcement learning and really the growth of meta learning. And that would include things like using built-in ML algorithms, automatic hyperparameter tuning, macro architecture search. All those kind of fit into sort of the automatic learning category of meta learning. And again, now our ML AI are managed end-to-end services and really bringing in turnkey solutions from third parties where they fit. And again, you see an expansion of backgrounds, including now ops people. 2020, it's hard to predict for certain, but two things we do know. We see now models moving upstream into the data area, the data engineering, and actually do data validation on our data before it's used for training. And we're anticipating an explosion on meta learning. So let's talk a moment about what kind of jobs that we have in 2020. So at the enterprise level, generally, you have two areas. You have your innovation centers and production. And innovation centers is where you're going to find the research data scientists. Our applied data scientists, the ones that are very senior, tend to straddle between the two. You find them in both the innovation centers and in production. And similarly with the machine learning engineers, both being in innovation centers and production. On the production side, we'll find our machine learning operations or ops people, our data engineers, and we sort of have a new emerging area called AI application engineers. These are your traditional software engineers that write applications. They're still software engineers writing applications, but they're now consuming the AI components that are produced. And then there is this sort of uncertainty still of QA. It's not certain exactly how yet QA fits in. So I'm going to give you an overview of what production was like in 2019. So you start off with some data that's been labeled. This is your training data, and it's going to go into a repository. And your data engineers are going to have a data distribution method, a way of preparing the data and feeding it just in time for model training. And we don't train a single model anymore. We train multiple instances of the model, trying to find which one is better. And even within that, on each instance, we do what's called warm-up training. These are little short-run trainings to do what's called numerical stabilization, which helps the initial weights in the model, get them to a point where they can better learn. So we're going to train several instances here. This is sort of our hyperparameter tuning. And we're going to find of those which one really was our best model. And that's the one we're going to fully train. At the same time, today we have model repos. They're like source code repositories where you store versions of your model. So when I train a model, I'm going to check it against a previous version to see if it's any better. And if it's not better, we're just going to repeat this whole process until we have a better one. But if it is better, then we're going to version it. So maybe a previous one was version 2, this one becomes version 3, and then we're going to deploy it. At this point, though, we really don't know for certain when the model is deployed in the real world if it really is better than the previous model. And so most companies now do something like A/B testing, where the previous version of the model goes to some customers and the newest version goes to others, and they have some performance metric to measure which model is doing better. And based on those metrics and observations, they're going to generate new data, goes into a repository, and this cycle repeats over, constantly updating and improving on the model. So I'm going to talk a little bit about what models are today. It's really not a single model anymore. We have this concept called model amalgamation. And prior, if you go back a little bit of time, how models were being used is you had an application, usually a back-end application on a server, probably written in Java or C#, and within the application, you would make calls out, these REST-based calls to these endpoints that were models. So that's how you consume them. Today, we put all the models together and in an amalgamation, and they're the entire application. There is no back end anymore. And to accomplish this, models are becoming more what we call multitask. They don't do a single task. Self or meta learning, actually models learning on their own. They share common layers and they connect via each other through embeddings. So I'll give you sort of an insight of how that works. First, for that all the work, models, we made it to model amalgamation because we started using design patterns. Okay, and this is a typical modern design pattern for a classifier and image classifier specifically. It's going to have a STEM component, a learner component, and a classifier. The STEM is where the images, the input images, are sort of being prepared, putting into a machine learning good state to learn from. The learner section is where we're going to learn the essential features. And I'm going to repeat this a few times. Today we learn not the data, but the essential features from the data. And then finally, the classifier is where we learn the task we want to accomplish. In this case, when we say a classifier, what something is. So when we talk about multitask models, it means that we're learning more than one task in the model, in that there are shared or common components within the model. So here's a typical object detection model. It has some shared components here, but we have two tasks here. One is a classifier, one is a bounding box. So first we want to learn what are the bounding boxes around the objects, and separately and independently, we want to learn what's inside that bounding box. So I'm going to give you some examples of real-world model amalgamations that we see when we work with our enterprise customers. So this is a typical one you see in sports broadcasting. So you have a sports game. It's a network broadcaster. They have a live video of it. That live video is going to go through what we call some shared convolutional layers. Okay. And those layers, the embedding that comes out of it, will go through an object detection model. And so this is frame by frame. And so in every frame, it's going to have, what objects are in the frame. And those object level embeddings then will go to another model and do face recognition. Who is the player in that frame? And for that, after that, that same embeddings, that same shared data would go to another model, do pose estimation. What's the player doing? Maybe he's standing and ready to bat. Okay, and then all that information, all the objects in the frame, who the player is, their pose, is all pulled together into what's called a dense embedding. And that is now inputted to another sequence of models. For example, one that predicts the action. What action is the player doing? They're about to hit the ball. From that, you can automatically generate captions for the image. And once we have a caption, our these broadcasters are in markets all over the world. And so those captions, another model can translate those captions into the target language of the various regions that is being broadcast to. And then finally, automatically, we can use another model to convert those captions to speech. Here's another example in the power transmission lines. So our utility companies do regular inspection of the transmission lines. And historically, it was very costly. What they would do is they would fly a helicopter, and you would first have a pilot, and then you needed two people inside. One is a spotter with the binoculars, and another person is taking notes. And you have the issue, of course, it's very expensive, the cost of the helicopter, the cost of the three people in it. It's a very slow process going from tower to tower, and there's a certain amount of human error. Today, we don't do that. We fly drones instead of a helicopter. They've automatically been pre-trained on where all the towers are and how to recognize them. They just fly on their own without an operator. They have object detection in them. They can detect all the various components on the tower. And from that, they've been trained to determine the condition of those components, to recognize things that are damaged or need repair, or even to do anomaly detection to try to predict when those items will need maintenance. And that, again, all of that together is the entire application. We work with a lot of enterprise companies that are in some way involved with homes. Okay, it may be the selling of homes, renting of homes, refurbishing of homes. And their clients and users are typically uploading pictures of their homes to their website. And historically, these would be manually looked at or evaluated. Even that is now being fully automated with models. And so typically when photos come up, some are going to be outside, the exterior, and some are going to be interior, specific rooms. So you might start with a binary classifier. It's going to say, is that photo an interior or an exterior? And I'll skip these little internal amalgamations for a moment, but what comes out of that is an embedding. And those would go to a final set of models, like a multi-class classifier, that would determine the market appeal. What demographic would want to buy this home, for example? The data might go through in parallel another model like a regressor that determines evaluation. How much should the house sell for, or how much should the house rent for? And it may also go through another regressor to determine renovation. What would be the cost of repairs? And then when we look inside of this, when we came out of that binary classifier here and we have that embedding and it goes into one of these, that embedding can now go to other models. So typically it's sort of a two-tier thing. We've determined first we're going to determine what type of room it is. And on the room, we're going to put it through a multi-class classifier to determine sort of the condition of the overall room. And then from that, from after we determine what type of room type, we're going to then look at what objects are in the room. The amenities, for example, if it's a kitchen, we're going to be identifying the stove, the oven, refrigerator, things like that. And then those little cropped out amenities can themselves go through another sequence of models to determine the condition, the market appeal, and the valuation on the individual amenities as well as on the room. And that all gets pulled together into a dense embedding. All that low-level information is collected up, and that's the final stage, which makes the overall determination of the market appeal or the valuation or the renovation. So again, all those models, the amalgamation of them, are the entire application. So I'll discuss some of the developments in commercial AutoML. So AutoML has came a long way since Google's paper on nascent, and there's a lot of services now available on the cloud. starting with transfer learning, or sometimes referred to as built-in algorithms, automatic hyperparameter search, macro architecture search, which is sort of a lesser form of what AutoML was for NASNet, a very cost-efficient way. It was used by Google to discover MobileNet v3. And then there's the microarchitecture search, that very detailed, somewhat highly expensive form that if a customer wants to use, we can make available. And then we're seeing automatic learning move into upstream into the data validation. Those techniques coming out of research, and we anticipate them becoming products this year. So built-in algorithms is really about taking pre-trained models and replacing that last layer, the classifier, or the layer that learns a task, with another task layer going to reuse the rest of the model and simply retrain it on that task. And one of the advantages to it is we can use a lot less data and we can train it much quicker. So in hyperparameter, automatic hyperparameter search, or sometimes called tuning, the big three are the learning rate, or more specifically, the learning rate scheduler, the batch size, and regularization. And this stuff is used to really get the best result of your model possible. Sorry for the noise in the background when we're all doing this from home. So the really big one is the learning rate scheduler. Okay. And today we just don't do like one training of a model. Okay. We're going to go through a series of steps called warm-up, pre-training, and model training. So in warm-up, we're sort of learning how to get the best weight initialization on the model. And then we're going to do some pre-training on the model, where we're not going to do full training. We're going to use partial amounts of the training set. We're going to try different learning rate schedules and try to find which one is going to, we think, give the optimal result. So we take that model sort of with the best weight initialization and the best learning rate schedule, and that's what we send to full training. We've also discovered that there are advantages to dynamically changing the batch size. Previously, we would do hyperparameter search to find the optimal batch size, but we would use it throughout the whole training. So it might be something like 32 or 128. What we find is that as we get deeper and deeper in training, and we're getting nearer and nearer the end, it's good to somehow be able to apply a smoothing factor to the data that we're feeding it. And by dynamically increasing the batch size as we get further into training, we actually implement that smoothing factor, and we get models that better generalize and are more accurate. And then finally, there's regularization. Okay. So in models, we tend to talk about them being large, or more importantly, over capacity. So for models to learn, they need a lot of redundancy. Okay. And one of the problems with the redundancy, or this overcapacity, is that some of those nodes inside of the model could actually learn to memorize the data, the example, or the images. And we don't want them to memorize, we want them to generalize. And the way to generalize them is by adding a certain amount of noise into the model. And previously, go back a few years, we did those things with dropout and noise. And today we do them with layer regularization, also known as weight decay, and label smoothing. So there's also a automatic hyperparameter tuning to find the ideal amounts of label smoothing and weight decay as regularization, so to get the best generalization out of our models. And now when we are designing models, we've kind of expanded the term of parameters. Historically, we said parameters to mean all the things that the model learns and stays with it. Those are like the weights. And the hyperparameters were all those parameters we use to train the model with, like the learning rate, like the batch size, but you don't stay with the model when they're trained. But today, because we bring in more and more automatic learning, as these models are training, they may also dynamically change their configuration. And how they dynamically change their configuration is the meta parameters. So with an example of a meta parameter, they're typically used what we call for the macro architecture search. And so they're going to modify the model at sort of a macro level. And that means like the number of groups that are in there and what's inside the groups. If we're talking about convolution, like how many filters inside of every group, or even what type of group is going to use, like a ResNet V2. So I'm going to talk a moment here about what's happening in data engineering. Okay, so previously we did our data engineering, or more or less like data pre-processing, upstream from training our models. And that meant we did it on the CPU. And the problem that became is our GPUs have gotten more and more and more powerful. And these CPUs are not able to keep up with feeding them. And so in a sense, we've started to starve the GPUs, not use them at their full capacity. So we've redesigned TensorFlow 2 to actually bring pre-processing into the model. There's all kinds of new layers that are specific to pre-processing. And from an architectural point of view, we see that as a pre-stem component, a component that's inserted in front of the stem where we do the pre-processing. Now that it's become part of the model, all the pre-processing is done on the GPU, and we're not starving them anymore. Another thing that we pulled into the model is translational invariance, and this is your image augmentation. So one of the things, the reason we automatically augment images, do random rotations and random flips and things like that, is we want the model to learn it doesn't matter where in the image the object is. It doesn't matter if it's on the left side, on the right side, in the middle, at the top, or at the bottom. And also zoom or scale, is it zoomed out or zoomed in? Again, we did all that stuff upstream on a CPU as we're training the model. We now have layers in TensorFlow that automatically do these translations, and those are put into the model. So the model itself learns the translational invariance instead of us training it to do it. I've said this before, but I really have to emphasize this. Today, when we're training a model, we're always talking about learning the essential features, not learning the data. We want to know what is it in those images that's essential to say what it is. Okay, and there are a lot of different techniques we use to assist us in learning essential features in addition to the full training. Very popular ones are using synthetic data, which are these pre-built data sets or generators, like from Unity. Occlusion, this is the ability of overlaying objects on items being classified. And then there's optical flow, and that's overlaying objects in the background. So let's talk about synthetic data, how it helps us. So let's say you have a data set of images of cars and you're training it to learn make, model, and year. Okay. Well, what we really want is, do we want to pre-train our model to learn what are the essential features of something even being a car? okay? And so what we would start with is synthetic data of cars, and we would train the model with those. And once the model, and this is an area we call representational learning, once the model has accomplished representational learning and knows now the essential features, we can now take that into a bigger model that learned with the real training data, the full training data, and learns the make, model, and year of actual real images of cars. So occlusion is kind of like helping the models to learn how to fill in missing parts of essential features that might be included. So for example, we may have trained a model for pedestrian recognition. But if that pedestrian is behind a car and we only see the top half of them, the bottom half is occluded. And so what we want to do is when we're training the model, for like that example, pedestrian prediction, we also like to use another data set which has occlusion objects that get overlaid and partially occlude at random the things we're training. And that helps the model learn how to fill in the missing parts of the essential features when they're occluded. And then optical flow is used to help the model learn what's not an essential feature, or in effect, what's a background. And we typically do this with geometric shaped objects that are randomly placed in the background. And there's a very popular data set for this called flying chairs. It's all kinds of geometric shapes. Many of them are chairs in odd and strange orientations that you use, and you just randomly place them on the background of your images. And when we do that, combine it with the real world data, it helps the model learn what's what isn't the essential feature. That is, what is the background. So I'll talk a little bit now about what we're doing in meta learning. And meta learning is moving into self-learning, models learning on their own. And ways that we do that or improve learning that are we see being used a lot right now are knowledge distillation, semi-supervised learning, and weakly supervised learning. And in these latter two, we're using them primarily with unlabeled data or noisy labeled data. So knowledge distillation is trying to solve the problem of we like to have compact models. These are small models that fit into memory constrained devices like your mobile phone or an IoT device. But if you recall, we get the good accuracy and the good quality in models by overcapacity, making our models large, and they're just too big to put on these devices. So what we do now is we use a method called teacher-student training, where we take a fully trained large model and we use it to train a compact model to mimic the big model, the teacher. And then it's the compact model, the student, that we put onto the memory constrained device. So semi-supervised learning is something we do when most of our data is unlabeled. So let's say you have a million pictures, okay, but only a small amount of them, maybe 10,000 of them are labeled. And you don't really want to go, or it's not practical to go through the expense of labeling all the rest. Okay, so what we do is we take that small amount of labeled data and we train the model initially to be reasonably accurate. Isn't that going to be great because it's too little data, but it'll have some good accuracy. Then we're going to run our once trained our unlabeled data through it to sort of guess what the label would have been for that data, and we call that our pseudo-labeled data. Then we combine it with our known labeled data into this composite training data. And it's the composite training data we then use to continually train the model, incrementally improving it. And every time we do a pass through it, we take that unlabeled data again, run it through because the model is better, and we get a better prediction of pseudo-labeled data, combine it with the labeled data. That's our next generation of composite training data, and we just keep repeating the cycle. In weakly supervised learning, we have a little bit of good quality labeled data, and we do our remainder of our data is labelable. We call it noisy. Okay, and noisy kind of means that there's inconsistencies about how it was labeled. That typically happens from crowdsourced data. So what we want to do is we're going to train a bunch of weak learners as an ensemble. And we're going to train them first with the good labeled data, and then we're going to further train them on the noisy labeled data. And once we've done that, we got sort of a pseudo-trained model here, and we got several of them that are going to vote what they think the label should be. We then run the noisy data through that, and it sort of re-predicts what the labels are under the presumption that the data coming out the other side is now less noisy, and we can combine that with the label data to build a stronger model. So I'll wrap up talking about ethical AI. So one of the areas we have to deal with is bias. Historically, you might have data sets that are demographically imbalanced. Okay, and so now when we have data sets like that and methods to determine that, we need to rebalance them. And so we tend to do that with resampling rules, where we take an imbalanced data set and rebalance it into a balanced data set so it doesn't have that demographic imbalance. And that's what we draw our batches from when we do training. Another area is fairness. Fairness is when there was some past cultural discrimination based on some cultural feature like gender or race or age. Even when we take that out of the data set, let's say gender, we find that the remaining features in the data set had collinearity to what we call the cultural feature that was discriminating. That is, they still, even without that element, even with that element removed, they still had, the features still reflected that discrimination, and you still ended up training a discriminating model. So today we take that discriminating data set and we use these synthetic generators that identify those cultural features and say the characteristics that are discriminating, and then generate new data that is non-discriminating or offsets the discrimination and is added to the other data to sort of rebalance it so that we have coming out the other end is a non-discriminating data set, and that's what we use to train. So in the final area here that's important is explainable AI. And that is, society's not going to trust models whose predictions can't be explained, audited, and justified. And at first, models were looked at as black box. And in some areas, this isn't going to work. If you think about it, if you used a model to determine whether somebody got a loan or not, or whether you would rent to somebody or not, in the past, that was all done by a human being. And if the person was turned down, that human being could tell them why they were turned down. And they could even tell them what they would need to do to change that decision. So like in a loan, you might need a better credit score or pay off this one debt. In a black box model, you just have yes or no, and you don't know why. So today, we take those black box models and we instrument them. That is, we put sensors, if you want to call it, inside the model to monitor what's happening in the model. How is it making its decision? And then in our instrumented model, that is what we make the prediction from, and it sort of generates like a heat map telling us how each feature contributed to the prediction, which ones were important in saying yes, or which ones were important in the result saying no. And having identified that, we can then actually look at those individual features and see how much they would have had to have changed to change the result. Again, if we use the loan example, how much your credit score would have had to have changed, or how much you would have had to pay off your credit card balance. So that's the end of our presentation. I want to thank you for all joining, and we'll move on to shortly to the next item.